Good day. I will present our work on a system for detection of various kinds of charts in documents and recovery of the underlying tabular data that the charts were produced from. This work is being conducted in IBM Research Lab in Haifa, Israel. The task we are solving consists of the following steps. Upon receiving a document page, it is required to find all the regions containing charts. For each such chart image, the task consists of recovering the numerical and textual data used in the chart construction, labels and heights of bars, sector of pies and their legends, numerical data of the line graphs, and so on. Finally, the output is the JSON file containing all the data that is required to construct the chart. So, why do we solve it? The described task is becoming more and more relevant in the light of recent research works and industrial products fusing the visual and textual domains. It is required to extend the document search from text only to graphical objects contained in the document and carrying important information. Specifically, this reconstruction enables question answering based on charts data. In general, analysis of charts is another step towards full analysis of the content of the scanned images. There is a number of previous works addressing the task of the chart data recovery, as well as directly approaching the task of question answering in charts and figures. We hope this work will contribute to the progress on this front. Our system is designed as follows. Upon receiving a document page, we engage an object detector that extracts regions of individual charts, as well as the textual elements associated with charts, titles, captions, and legends. This is done on the page level, as in some situations there are groups of charts sharing the title or the legend. Next, a different detector extracts graphical objects in the chart image. This is done in two forms. We extract predictions both in form of boxes for bars and legends and in form of image-sized heat maps for elements of pies, areas of line graphs, and so on. In parallel, an OCR module retrieves the text elements in the image for labels and numerical values. We use the Detectron 2 framework for the two detectors, where the Stage 1 detector is trained with manually annotated chart and text regions in real-world documents. And for Stage 2, we use synthetic data consisting of many thousands of chart images. It is an extension of the Figure QA dataset, generated by adding various degrees of freedom, random backgrounds, line colors and styles, and so on. Finally, there is a number of computer vision-based analysis algorithms, each dedicated to each chart type. They combine the information from the detectors, find necessary geometric and spatial relations, extract numerical values and labels of the relevant objects, and produce the final output in the JSON format. Standard object detectors are trained to predict object locations by producing box proposals in the image. However, for the pie charts, for example, this doesn't work very well. Even if the sector boxes are well predicted, it is hard to extract the sector angles. For a line chart, boxes just won't do. We need the specific pixels of the graphs in the line. Therefore, we use a centronet detector that allows heat map prediction. For example, if I want the detector to help me find the radial lines in the pie chart, then during the synthesis of the pie chart image, I also render an image of the same size that contains just the black and white radial lines in the same locations as in the full chart image. Then, after applying the smoothing operator, this image serves as ground truth map that needs to be matched by the detector output. In this fashion, we can train the detector to predict the pie circumference, the center, and the radial lines. For line and scatter charts, the heat map highlights the graph data. In any charts, we have dedicated heat maps for X and Y axis and for the ticks on the axis. These heat maps enable the downstream computer vision algorithms to find the relevant graphical objects, pie circles and sectors, line curves, etc. This allows us to support bar charts, pie charts, line and scatter charts. After detecting the graphical elements, we associate them with the recognized textual elements, such as axis ticks, labels, and legends, and provide value and label to each chart component, such as bar and pie sector. While there exist works that address this step with a neural network processing and perform the entire chart understanding as a neural pipeline, as mentioned in our paper, we have decided to perform this operation with explicit engineering, considering the many designs and variations of charts and their components we have encountered. A lot of efforts were invested in the algorithm for analyzing the y-axis with the tick values, in order to convert the pixels to numerical values in bar and line charts. Mostly, this is a challenge for the OCR engine that needs to deal with the tiny fonts, exponents, and special characters at the tick values, especially in the scientific papers. We have adjusted the OCR process to address these issues. Another one of the challenges is to recognize the legend entries, as the color samples are often tiny and corrupted with compression artifacts. Also, sometimes the pie sector labels are given by texts adjacent to the sectors, or even located remotely and associated with the sector by line connectors, and we had to add algorithm that deals with that. We intend to extend the support to pattern legends as well as the color legends for pie and bar charts in the future work. In the bar charts, there is an additional difficulty of detecting very small bars, lacking the example at this slide on the right. Additionally, we have pioneered the analysis of the line charts and encountered a number of difficulties in recovering the underlying numerical data. We start with the image area occupied by the graphs, as predicted by the corresponding heat map, and cluster this set of pixels by color, assuming different colors for each graph. Then, a tailored stitching algorithm pieces together a continuous line representing each graph and recovering its y values with the aforementioned numerical y-axis. In future, we intend to extend the support to different line types. We have carried out quantitative evaluation of the system on bar and pie charts, using real-world chart images from ICPR 2020 challenge data, where we have manually annotated the pie charts in full detail and have used the provided annotations for the bar charts. Both our detection stages, as well as the algorithmic analysis, completing the data extraction, are shown to work well, competing with and outperforming previous works. When comparing with the few available benchmarks on real-world data, we consider different levels of numerical accuracy for the extracted values, as well as different levels of strictness for the recovered labels. Beyond the reported experiments, we have evaluated the system on large corpora of scientific and financial documents, observing good general performance as well as number of special cases that defy general treatment. I will be glad to answer any question related to our work via the email address given in the paper. Also, please come visit our group homepage at the presented address and learn about additional projects our group is conducting. Thank you all for your attention.